Howdy y'all, this is Braden Miller. I am a PhD student at Texas A&M University in the Material Science and Engineering department, and today I'm doing a presentation for MSEN 660's Journal Club over unsupervised learning. The paper that we'll be going over today is titled Identifying Structural Changes with Unsupervised Machine Learning Methods. It was written by Nicholas Walker, Calming Tom, Brian Novak, and M. Jarrell. They are all located at Louisiana State University in Baton Rouge, and they wrote a pretty cool paper. The work focused on identifying the first order transition from solid to liquid and then liquid to solid in two metals. They chose titanium and aluminum as examples of BCC and FCC metals, and they used molecular dynamics simulations of approximately 110 atoms. I think it was 108 and 120. I think the 120 was titanium, and I believe the 108 was for aluminum. And these systems were heated from several hundred Kelvin below their melting point to several hundred Kelvin above. This happened approximately over, I believe it was 9 nanoseconds. And they sat at their initial temperature for about 2 nanoseconds, ramped to their above melt temp over about 9 nanoseconds, sat there for about 2 nanoseconds, and then ramped back down to their original temperature over another 9 nanoseconds. These simulation time steps were approximately 0.004 picoseconds each. And then the MD simulations generated energy, pressure, volume, and atomic position data, which was sampled every 32 time steps, which was roughly every eighth of a picosecond. And that led to their data set, which they used in their machine learning, which we'll get to in a moment. On the right here, you can just see a rendering of just a generic molecular dynamics simulation of water molecules. I don't have any figures of what their work looked like, though I would be interested to see how it moved around in space. So, with their data that they pulled from their molecular dynamics simulations, they calculated the radial distribution functions for each atom, and then they clustered these using k-means. And on the right here, we have a plot of the centroids, or the radial distribution function of the centroids for the k-means clusters for their unreduced titanium data. And as you can see here, they have two temperatures. One is below melt temp and one is above. And both are reminiscent of the radial distribution functions you would expect in BCC materials, though they do have some smoothing and a little, some weird features. However, the RDFs provided a very distinct change in a pattern that machine learning is very capable of recognizing. And again, like I said before, the k-means centroid RDFs were very consistent with the expected BCC and FCC equilibrium structures, both in their solid phase and in their liquid phase. So the machine learning portion of this, they employed PCA to reduce feature space dimensions to 2 dimensions because it was significant. It was at least 6 from what I read in the paper. And then they used k-means clustering with 2 categories. This was meant to represent the liquid and solid phases in the materials. And then, sorry, after clustering, they went and used both geometric and arithmetic averages to estimate the melting point, and they actually managed to get these within 10% of the actual value, which may not sound like quite a lot, but it's actually kind of impressive because this is more meant as a proof of principle. And as we saw earlier, they are working with very, very small molecular dynamic simulations, and in the paper they do mention that they believe that with larger molecular dynamics simulations, they think that they could get better accuracy. And I personally believe that they might be able to get better accuracy if they were to extend their ramp windows. So instead of 9 nanoseconds, if they could do something slightly more realistic potentially, but who's to say? And then the new parts of all of this to me was using centroids of clusters to simplify radial distribution functions. I had never seen that before. And it was interesting to me that even the centroids of all of these radial distribution functions still managed to represent what you would see in when calculating a radial distribution function of a crystal lattice. And then I had also never seen anyone use k-means to identify a structural change. I've heard of using unsupervised learning to identify um, like grain boundaries and stuff like that. We discussed that in class. I had never seen anyone calculate all these radial distribution functions and then use k-means to actually like estimate where the melt point would happen. And then I had also never seen anyone utilize the change in RDFs as something that a machine learning algorithm can identify, and it really has got my brain going on just calculating RDFs in a way that you can teach machine learning what these different phases represent on a phase diagram. And to me, it feels like you could almost use it to teach a machine learning algorithm kind of how to navigate a phase diagram. And it would take a lot of computational power, but if you could set up machine learning to sit there and turn the knobs and be able to calculate these RDFs, or turn the knobs on a molecular dynamics simulation and then calculate the change on these RDFs, I think you could get really interesting results because you could wind up with like processing maps and stuff. But that's all speculation. I'm kind of rambling and I've hit my time limit. So I thank you for your time and I hope you join me again next time. Thank you. Any questions? Except you'll have to leave them in the comments because this is a recording.